And let's do chapter 27, problem 33, which is right here. Nope. Okay. All right. Here we go. The problem says, all right. If we know everything that's given to us, what's the EMF of this battery? So let's start there. This is basically saying, it's saying the following. If this number right here, if the current going through R6, if this equals 1.47 amperes, what's the battery voltage? That's what this question is saying. What's battery's voltage? All right, so now again, let me read that again. If the current going through resistor 6 is 1.47 amperes, which it is because that's given, what's the battery voltage? What battery voltage do I have to have if I have 1.47 amperes going through R6? So let me just erase all that. So all right, so let's go ahead and talk about that term EMF. I guess I need to erase this. EMF, that you see that script letter E? Erase. All right, so this is in the green sheets, but right now there is a term called EMF, script E. So number one, this script E stands for electromotive force. EMF, electromotive force. So, oh, come on, pen. Darn it. Oh, well. EMF. And electromotive force, it's kind of an archaic term, but we still use it. It's basically, it's voltage associated with a source, All right, there are voltage drops across a resistor. So again, you know, if I look at R3 here, there's a voltage drop associated with R3. So there's a, you know, the voltage at the top of R3 is different from the voltage at the bottom of R3. So there's a voltage drop or a voltage difference across R3. But R3 is not a source. This is a source. A battery is a source. You know what else is a source? A generator, a fuel cell, a photoelectric device, a thermoelectric generator.
So it's basically asking for the battery's voltage.
Yeah, it is. And I just wanted to hype the fact that EMF is going to be persistent going forward. And it's kind of easy to not understand what it is, but now you know it's associated with a battery, which is a chemical source, a photovoltaic device, which is a quantum mechanical source, and a thermoelectric device, which is a semiconductor source, so on and on and on. But it's the key word here is source. Because you can say, well, I have a voltage drop across R3, but that's not a source. So that does, you call that a voltage drop, not an EMF. Anyway, let's go on. So that was exhaustive. Let's go ahead and start analyzing the circuit. We got to figure out what that battery voltage needs to be. All right, so I'm going to actually make this a little bit bigger. When you make your circuit drawings, suggestion, make them really large, which is what I'm going to do right now. Otherwise, it gets very crammed. All right, so there. Let me erase some junk. All right. So here goes. All right. Well, I'm just going to start adhering to my rules. I know that this must be a positive terminal. Okay, I guess. To be honest, you guys, it does help to have multiple colored writing instruments. All right, so, well, I know that's positive. I can be done with that. That must be positive. That must be negative. Why? Because of the convention. Current always flows into a resistor's positive terminal and exits the resistor's negative terminal. You know what? This has to be plus. That has to be minus. I don't even have to think about it. It just is because they're in series. That's a series connection. The other thing I can say here is I know that this also must be I6. Same current, series connection. The current flowing through R5 must be the same as the current flowing through R6 because they're connected in series. So I got a lot out of that. I know my positive terminals, negative terminals. All right, so I6 equals 1.47. My numbers, you have different numbers. 1.47, I should say, 1.47 amperes. I'd like to color code it as mentioned. So I'll go to this color. R6 is, I6 is 1.47. R6 is given to us as 3.85 ohms. 3.85 ohms, fine. Another color for V6, the voltage across that resistor is going to be, I don't know. So I guess now let's bounce into Ohm's law. Number one, Ohm's law says this, says V equals IR generically or generally. So specifically, the voltage drop across resistor 6 equals the current going through resistor 6 times the value of resistor 6. The current going through resistor 6 was given as 1.47 amperes. The resistance of resistor 6 is 3.85 ohms. So, and then we definitely have to store things in calculator. So I've got 1.47 I times 3.85 ohms, or 5.6595 volts. 5.6595, store alpha A for sure, but I'll write it down here for record keeping purposes. 5.6595 volts. So there it is. There's IRV. So we're just going to do IRV, I for current, R for resistance, V. We're going to do that for every circuit element and just adhere to conventions. 5.6595. So that's that. Let's do this. I know I6, so let's just keep going here. I know that this is also equal to 1.47. Got it. Let's do this resistor value is R5. R5 is 7.20. R5 is 7.20 ohms. Yep. And then let's go to voltage. This is another job for Ohm's law. My voltage across R5 is just Ohm's law, and maybe I'll fast track a little bit, but my voltage across R5 is the current going through 1.47. 1.47 amps is going through R5, which means it's burning up. R5 is burning up some voltage, 1.47 times 7.2 ohms. This is SICM A. I don't want to forget about that. SICM A. So I have 1.47 times 7.2 is 10.584. 10.584 volts. Let's add that to the schematic. 10.584 volts. Good to know. Now for the loop rule. Here's Kirchhoff's loop rule. I'm just going to call it loop rule. Loop rule says this. Loop rule says that whatever that voltage is across R4, my voltage across R4 plus my voltage across R5 plus my voltage across R6, whatever they add up to be, it equals 0. And you might be thinking as I am, but it's just not the convention. But you could say, Chris, shouldn't you say the change in voltage across, and this should be R4. Sorry. Let me erase. All right. R4. So again, this would be maybe acceptable. Whatever the change in voltage is across R4 plus whatever the change in voltage is across R5 plus whatever the change in voltage is across R6. And I can see here, just for consistency, just for the sake of consistency, let me erase that just so I can be uniform. All right. And it's fine, equals 0. All right, so you know what that means. Let's do this. So the voltage, I guess I'll do it like this. This may be pretty good. My voltage change across R4 is going to equal negative of the voltage change across R5 minus delta V6. With numbers, I have negative 10.584 volts minus 5.6595 volts equals 10.584, 5.6595. And I hope you guys are doing this, because then that way you'll for sure be able to tell me if I'm making a mistake. Negative 16.2435 volts. And that's great. So right now, you guys, you know what the positive terminal is for R4. This is a major step. All right, so shout out one way or the other. Is this positive, or
yes?
Sure, you don't want to think about it. Is this positive, or is this negative, or is this I don't know, or is this I don't care? But this is positive. So that has to be positive. That has to be negative. Otherwise, this wouldn't work. This is basically saying this says positive on top.
So the fact it's negative means that the current's flowing opposite the direction that you've drawn the loop.
Not yet. The only I can't come to that conclusion yet. The only thing I can say right now is, well, no, maybe you're right. Maybe I didn't quite understand your question, because maybe this is what you're doing, Chris. Chris is saying, I think, let's hire Probert. So we're going to rehire Probert. If I rehire Probert says, well, okay, this is a positive 16.2435. But now I'm losing 10.584. And now I'm losing another 5.6595. And then that's why I get delta V equals 0. Because once again, let me just repeat that. Probert starts down here at the bottom of Mount Everest. Probert gets an energy boost, but then that part of that energy boost is burned up by R5. And then part of the remaining part is burned up through R6, and then leaving 0. So Chris, that's probably what you were referring to. But is everyone clear on that? Because this is I need to spend an enormous amount of time because this is the fundamental stuff. This is the type of stuff that if you're unclear, then, you know, then it's going to be a long, cold, lonely winter. All right, anyway, so now I know my current direction. Great news. I know how to draw my current. I'm going to draw my current going down. Ta-da! I know that has to be the case. So I'm just going to call this I4. And I say, I guess I'll stick to try to stick to capitals. I4. I know that's has to be the current direction. All right, so IR4 equals, we're going to have to get a number on that. But right now I do know the voltage. So back to blue. Let's go to blue. I do know that this voltage across R4 equals 16.2435. 16.2435 volts. 16.2435. Blue for voltage. I got blue. I need the resistor value, which I know what that is. R4 is given as 16.7 ohms. 16.7 ohms. So Ohm's law to the rescue. If V equals IR, then I equals V over R. So number 4, Ohm's law. Ohm's law says V equals IR, which means I equals V over R. And I know the voltage, it's 16.2435 volts. And I know the resistor value, it's 16.7 ohms. So let's divide those. 16.2435 divided by 16.7. 0.972, 0.9726, and I'm actually going to store this. I haven't been storing some of these. Some of these have a finite number of decimal places, but I'm definitely going to SICM this. This is going to be SICM B. Store alpha B. Store alpha B, because that's a hairy number. All right, so then I can write down 0.9726 and some change amperes. Good to know. Now we can do junction rule. This is junction 1. I'm going to label this junction 1. And I know Kirchhoff's junction rule says that the current flowing into a junction, this is the current flowing into a junction. I'm going to label this current going through resistor 2. So I2 is flowing in, I4 is flowing out, I6 is flowing out. So, and the only way we can say this with certainty is by doing what we did. You can't, I mean, there might be other ways, I don't know, but right now we have proved definitively that I4 is in fact physically going down and I5 is physically going to the right. So let's do Kirchhoff's junction rule, which says in equals out. What's going in? IR2 or I2. I2 is going in. Anything else going in? Nope. What's coming out? I5 plus I4. So I have the current flowing through resistor 2 into junction 1 is I5, which I had up here as 1.47. Oh, here's a little typo, you guys. Well, maybe not a typo, kind of a typo. I'm going to say I5 equals I6. All right, just that kind of caught my eye. All right, so I2 is equal to 1.47. Apparently I'm changing colors. 1.47 is coming out. Also, that 0.9726 plus SICM B is coming out. So this is IR2 plus 1.47 is 2.44 and some change. 2.4426 amperes SICM C, store alpha C. Okay, we're just working backwards. All right. So I'm going to do my terminal. I've got, this has to be a positive terminal. This has to be a negative terminal. I2 is equal to 2.44 and some change amperes, just running out of real estate. Let's talk about R2. R2 is 1.66 ohms. So I'll use red for that. R2, I'm going to erase something. I can't. R2 equals 1.66 ohms. And let's use Ohm's law, 1.66 ohms. All right, so blue for voltage, V2 equals IR. So just, you can do that right now, but I'll fight the good fight and do it. The voltage across resistor 2 is the current going through resistor 2 times the value of resistor 2. The current going through resistor 2 is SICM B, or SICM C, I should say, for me. So I'm just going to do SICM C times R2 1.66. All right, so multiply that times 1.66, 4.05 and some change. 4.05 volts, SICM D, store alpha D. I probably don't have, I don't think I need to use new memory locations, because once we get these values, I think we can leave them behind. But 4.054 and some change, everything. So we're doing IVR for every element. 4.054 volts. And this again is SICM D for me. All right, so fine. Now we have the same conversation. Now we're going to do another loop rule. Here's a loop. Ready, set, go. It doesn't have to be clockwise, but just out of habit, let's just always do clockwise loops. So here's a loop. That's a loop. So rises equals drops. So for that loop, let's do Kirchhoff's loop rule. Loop rule says that my change in voltage, I guess I better erase this a little bit. That's R3, I guess. Let me erase. That's good. Okay, that's good. That shows well. All right, so I got R3, R2, and R4. So loop rule, which is conservation of energy, is saying whatever the voltage is for 3 plus whatever the voltage is for 2 plus whatever the voltage is for 4, it's got to equal 0. So my voltage across 3 equals negative V2 minus V4 equals negative V2. My V2 was 4.054, which is SICM D. So I'm going to do negative SICM D minus V4. My voltage across resistor 4 was at 16.2435. 16.2435. I didn't store that just because it's finite. All right, so this equals negative plus 16.2435. 20 and some change 20.298. And I'm just going to go back to A. I'm going to put that back in store alpha A, 20.298. All right. So R3, blue. This, playing that same game, you guys, and I think of this as a game. The only way that delta V can be equal 0, if this is positive, so right here, if this is positive and this is negative and this is positive and this is negative, the only way they can all sum to 0 is if this is positive and this is negative. So let's go ahead and do the IVR for all of this. My voltage across 3 is equal to, let me move this. Voltage across 3 equals 20 point and some change, 20.29. That's good. My resistor value is R3 equals 1.66 ohms. And then my current is Ohm's law. So I'll write it down, but I'm just going to do an on-the-fly calculation right now. Current is green. So Ohm's law says that I3 equals V over R. So I'm just going to do V over R 20.29 divided by 1.66. This is 12.27. Lots of current there. 12.27 amperes. All right, and then I'll show the work down here. Ohm's law. Ohm's law. Well, I equals V over R. So specifically, the current going through the resistor labeled R3 equals the voltage drop across R3 divided by R3. The voltage drop across R3 was that 20.29 number, which is SICM A, divided by R3, which is 1.66 ohms, equals 12.2279 amperes. And then I guess I'm just going to put this in SICM A again. All right, store alpha A. Notice I didn't bring along this negative. Well, I should have said this. I should have said therefore V3 equals 20.298 after we did the adjustment, or just the way we represent it. All right. That's that. We're so close now because we have all IVR characteristics for all resistors except for this one. I do know, except for R1, I do know this must be my current direction. Current always flows through from a resistor's positive terminal to the resistor's negative terminal, or out of the resistor's negative terminal. I'm going to call this junction 2. Here's J2. J2. Okay. I know right now I can say without any doubt whatsoever that current must be flowing into J2. Wrong color. All right, so I can say with certainty there. I know it has to go rightward through R1. Why? Because I have current flowing out of J2 going through R3, and I also have more current coming out of J2 going through R2. So there you go. That's proof positive. So this must be positive. This must be the positive terminal. This must be the negative terminal. R1 has a value of 1.66 ohms. So I'll just say R1 has a value of 1.66 ohms. What else do I need to know? Oh, I can use the junction rule to get the current. Current, we use green. All right, so I1 equals, and I'll write this down, but I can do what goes in I1, what's coming out, that 12.277 and some change, SICM A plus I2, and I2, and I should have kept that. I2 is SICM C, okay, plus alpha C. All right, 14.67 and some change. 14.67 amperes and some change. So let me draw that up. All right. Junction rule. So you just see just a succession of junction rule, loop rule, Ohm's law. Junction rule, loop rule, Ohm's law. Junction rule says in equals out. What's going in? The current flowing through resistor 1. Yep, isn't that right? Yeah. And what's flowing out? 3 and 2 equals the current flowing out through resistor 3 plus the current flowing out through resistor 2. The current flowing through resistor 3, we just figured that out. That's 12.27 and some change, which I had in SICM A, plus the current going through I2, which is 2.44 with my numbers, but I had that sitting there in my calculator somewhere here, 2.44. Where did I see that? I said SICM C. Where did I IR2? I2 2.44. Maybe I didn't write that down. Let me check. All right, plus 2.44. Oh, there it is. It is SICM C. I just wasn't. All right. So I had this sitting in my calculator memory in C, and then I had I3, which we just figured out is here, sitting here in A. And that's how I get my 14.67 number. Amperes. Okay. SICM A again, I guess. Is that, should I use A? All right. No, I'm going to use D. I guess I should have just kept using different memory locations. Store alpha D. All right. Blue for voltage. So my voltage across resistor R1 is found using Ohm's law, V equals IR. So V equals 14.67, which is calculator memory location D times R1, which is 1.66, or V1 equals 24.353 volts and some change. I'll store that in a memory location. And one last loop rule. Going clockwise around this loop, I can see that the voltage gain I get from my battery, my EMF, minus the voltage drop across resistor 1, minus the voltage drop across resistor 3 must equal to 0. So this is my final EMF value. If I have a battery with this voltage, I will get 1.47 amperes flowing through resistor 5 and resistor 6. That's it. The solution to this problem really does a good job reinforcing Ohm's law, the loop rule, the junction rule, and a lot of conventions.